All right, so surprise, surprise, Chapter 4, more graphing of rational functions. So in the warm-up today, we're going to look at some functions that you have seen and graphed. And so what we're looking for is the horizontal asymptote and the vertical asymptote of each function. Now, I'm going to start with the vertical because I think the vertical is the easier one. When I look at a vertical asymptote, I want to look at where the graph is undefined for x. That means what's going to make the denominator equal to 0. So when I look at this first function, I know that the value of x equals 4 would make that function undefined. In the second one, I know that the value of x equals 6 would make that undefined. X equals. In the third one, I know that the value of x equals -1 would make that undefined. In the third one, you might be able to figure that one out in your head pretty quickly. But, 2x minus 6, you can always take the bottom, the denominator, and set it equal to 0 and solve it. If you add 6 to both sides, you get 2x equals 6. Divide out the 2 on both sides, and you get x equals 3 here. So there is my vertical asymptote, x equals 3. Same thing with this last one, 2x squared minus 8. So we have 2x squared minus 8. And I can set that equal to 0. I can add 8 to both sides. That's 2x squared equals 8. Divide out the 2. That's x squared equal to 4. If I square root both sides, I get x equals plus and minus 2. So I have two vertical asymptotes here. X equals positive and -2. All right? So, going back to the top here for horizontal asymptotes. So, when we have a horizontal asymptote, what we're asking for is that what does this function equal as x approaches positive or negative infinity? What does the graph get closer and closer to? So, and again, if you need to, I would pull out a graphing calculator and graph some of these if necessary. But when I look at this function here, I see 2x divided by x, and I'm going to ignore the -1 and -4, because as x gets really big, subtracting 1 or subtracting 4 really doesn't make much of a difference. So as x goes to infinity, I end up with 2x over x, which is 2. So my horizontal asymptote would be y equals 2. Same thing in the next one, 3x over x, that's going to be y equals 3. So as x gets really big, my graph is going to approach 3. As x gets really small, my graph is going to approach 3. 5x over x, again, adding 1 doesn't make any difference when you're out at 1,000,000. If x was 1,000,000, this would be 5,000,000 over 1,000,000 and 1, which is basically 5,000,000. So y equals 5. 3x over 2x, I get y equals 3/2. We've got some squared terms here. X squared over 2x squared. Because the degree of the numerator is the same as the degree of the denominator, I can simply divide them out. This is 1x squared over 2x squared, so that's going to be y equals 1/2. All right? So, rational function, again, going back to the definition of a rational function, v of x is 1 in the form of f of x equals p of x over q of x, where p of x and q of x are polynomials, and q of x cannot equal 0. That's the big thing. We want to make sure that our polynomial in the denominator never equals 0. So, to find our vertical asymptote, we're going to take the denominator, q of x, all right? This is the denominator. Set the denominator equal to 0 and solve it. You could have more than one solution, just like our x equals plus minus 2 back up here, all right? Any graph of f of x has at most one horizontal asymptote. So in a rational function, you would have one asymptote. If the degree of p of x Okay, so this is the numerator. If the degree of the numerator is less than, all right, so I'm just going to, I'm going to use less. Yeah, less. Less than the degree of q of x. Again, this is denominator. So if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote. So that would be a situation of f of x equals 2x minus 6 over x plus 7. That's x to the first in the numerator, x to the first in the denominator. Oh, excuse me. This one's less than. Excuse me. Back up, back up. Let's call it 6 over x plus 7. The degree of the numerator is 0 because technically it's x to the 0 up there. There is no x there, okay? And then x to the first in the denominator, so this would go to 0. I was thinking about the second one here. If the degree of p of x, the numerator, is equal to the degree of q of x, the denominator, and the line y equals a over b is a horizontal asymptote where a and b are the leading coefficients of p of x and q of x. Let me go back to my previous example. F of x equals 2x minus 6 over x plus 7. When we talk about a and b, a is the lead coefficient of your numerator, so that would be 2. B is the lead coefficient of your denominator, that would be 1, so the horizontal asymptote would be y equals 2. And then if the degree of p of x is greater, so if my numerator has a degree that's greater than my denominator, then f of x has no horizontal asymptote, and we will graph those. So if I had f of x equals x squared over x minus 1, there is no horizontal asymptote. We actually get a slanted asymptote in that case. Holes in the graph of f of x. So if p of x and q of x have a common factor, so if I can factor the numerator and the denominator, and let's just say that that factor is x minus r. Okay, so if I see an x minus r in the top and the bottom of my fraction, then I would take that x minus r, set it equal to 0, and it would turn out that I have a hole at the value of x equals r. So for example, if I saw in my fractions an x minus 3 in the top and the bottom, I could take that out, set it equal to 0, and solve it, and I would have a hole at the value of 3 comma something. And we will talk about how to find the y value for that in one of the later examples here. Okay? So I'm going to stop here for a second. All right. A little drink of water always helps. Here we go. So example number 1. So to graph one of these guys, number 1, we want a horizontal and vertical asymptote. Horizontal comes from the lead coefficient. So the first thing I do is I look at these guys here, and this is 2x over 3x. So this is going to be an interesting one already. So I have a horizontal asymptote at y equals 2/3. For my vertical asymptote, I take my denominator. I take 3x plus 1, and I set it equal to 0. I subtract 1 on both sides, and I get 3x equals negative 1. I divide both sides by 3, and I have a vertical asymptote at x equals negative 1/3. Let's graph both of those right now. So y equals 2/3 is, whoops, not sure what happened there. All right. So y equals 2/3 is going to go right about here. Doesn't have to be perfect. All right. So there's y equals 2/3. X equals negative 1/3 is going to come down right here. All right. Now we can't do domain and range until we finish up, but we need some points for this graph. And those points are going to include x and y intercepts, and then if I need to, I'll do a little t-table. So we're going to start off with y intercepts. Easiest one to find. I plug in 0 for f of x. F of 0 equals 3 times 0 plus 2 over, oops, excuse me, that top one's a 2. 2 times 0 plus 2 over 3 times 0 plus 1. And the zeros cancel out, so all I'm left with is 2 over 1, so that's 2. So I have a y-intercept at 0, 2. So I'll plot that. 0, 2 right there. All right. X-intercept. Let's do a different color for this guy. Let's go to green. X-intercept. This one takes a little bit more work. So we have 0 in for y equals 2x plus 2 over 3x plus 1. I want to cross multiply this. So if it helps you, you can always put 0 over 1 to see that cross multiplication. So I multiply 0 times anything. So 0 times 3x plus 1 is just 0. Throw an equal sign in there right away. 1 times 2x plus 2 is 2x plus 2. Now I'll give you a little hint right here too. Anytime you're finding x-intercepts on a rational function, they always come out of the numerator right here. Always. I don't even care about the denominator. X-intercepts come out of the numerator. So we're going to solve this. We're going to subtract 2 on both sides here. So this is negative 2 equals 2x. Divide out the 2 and you get x equals negative 1, or the point negative 1 comma 0. So let's go plot that. So I have a point on either side here. Now if I know what the graph looks like, I can graph this right now. If I'm not quite sure what to do, I would go and maybe do a small t-table and just do maybe a couple other points on either side of the vertical asymptote. So I'm going to do x and y, and I'm going to pick one more to the right. So I'm going to pick the value of x equals, and I'm just going to go with 1, and then I'm going to go with negative 2. If I plug in 1, I will get, let me see here, if I plug in 1. Hang on a second, let me do the math and not waste your time here. I actually get 1. So I get the point 1 comma 1. All right. If I do negative 2, I get, well, let's just do it over here on the left. That'd be 2 times negative 2 is negative 4. Negative 4 plus 2 would be negative 2 over 3 times negative 2 is negative 6 plus 1 is negative 5. I get 2/5, positive 2/5. Wow. All right. So negative 2 gives me positive 2/5. And so now I've got a pretty good idea of what, where this thing's rolling. It's very tightly curved into the corner there where the asymptotes meet. And there's my graph right there. Based on that graph, I can give a domain and a range. A domain, x in the set of reals. That graph goes all the way left, all the way right, but it jumps over the value of x equals, where's my vertical asymptote? Negative 1/3. The range, x or y in the set of reals. Y in the set of reals. But I'm going to jump over the value of y equals 2/3. So we need to exclude that in our range. Okay. Next one, here we go. All right. So this one here, horizontal asymptote, I can do that from the regular equation. So I look at my equation, I see 2x squared over x squared. I divide those out and I get y equals 2. Vertical asymptote, a little more difficult in this case. So what I want to do now is everything else I do with this equation, I want to factor it. So I'm going to factor the numerator and I'm going to factor the denominator and figure out what to do next. So f of x, if I factor the numerator, I get 2x minus 1 and x plus 2. If I factor the denominator, I get x minus 3 and x plus 2. So I now know that I have a whole because I have a pair of factors that will cancel each other out. So this right here tells me This implies factors that cancel, okay? So factors that cancel create holes. So where is that hole? That hole is at x equals -2. Now, how do I find the y value of the hole? I take my function, we call this hole, these x plus 2's, we call this a removable discontinuity, okay? A hole is someplace where you removed a discontinuity. I'm going to remove those x plus 2's out of my equation right now, and I'm going to rewrite it as f of x equals 2x minus 1 over x minus 3. Because once I know where the x value of the hole is, I never need to look at those factors again for anything. I'm going to use this new simplified equation for everything else that I do. Look, let's go to vertical asymptote. What value makes that denominator 0? X equals 3. Look at that. How easy was that? Where's the hole? The hole is at -2, and I need to find the y value. And now that I've removed the x plus 2's out of there, I can plug -2 into this function. So I'm going to find f of -2. That's going to equal 2 times -2 minus 1 over -2 minus 3. So I know that the whole, this is going to be -4 minus 1 is -5 over -5, which equals 1. That's the y value of my hole right there. So right away, before I do anything else here, I'm going to go to -2, +1, and I'm going to draw a hole. All right? Horizontal asymptote, y equals 2. We'll go ahead and graph that. Vertical asymptote, x equals 3. We'll go ahead and graph that. Y-intercept, let's find that. All right, here we go. Y-intercept. Plug in 0 for x, and again, remember, I'm not using the original function anymore. I'm using the simplified function. So take a look at the simplified function here. I know the y-intercept is 0 for x. Look at this function up here. 2 times 0 would be 0, so that's going to leave me -1. 0 minus 3 is going to leave me -3. So this is -1 over -3. So I have a y-intercept at 0, +1/3. You know what? I can draw the left side of this graph right now without doing any more work. But let's finish up. Let's find some x-intercepts. All right. This time again, 0 for y equals 2x minus 1 over x minus 3. I'm going to put a 1 under the 0. I'm going to cross multiply. 0 times x minus 3 is 0. 1 times 2x minus 1 is 2x minus 1. Remember what I told you on the last example? Your x-intercepts always come from the numerator of the rational function. I could have just set 2x minus 1 equal to 0 right away and found my x-intercepts. I'm going to add 1 to both sides. That's 2x equal to 1. Divide out the 2, and I get x equals 1/2. So I have an x-intercept at 1/2, 0. 1/2, 0. Look at that. Don't even need any more points over here. Graph's going to do something like that. What might be helpful is a point or two on the other side. So let's go to orange, and the other side I'm going to choose the values of 4 and 5. So I would just do a little t-table here, x and y with 4 and 5 in here. All right, and let's see, I'm gonna have to check my math again here. Hang on. So if I plug in 4, I'm actually going to get 7 out of the function. If I plug in 5, I get 9/2, which is equal to 4.5. All right, so I know I can graph the point 4, 7. which is going to go off my graph a little bit. That's all right. And 5, 1, 2, 3, 4.5. And if you're not happy with those, graph a couple more. It doesn't matter to me. You can pick whichever values you want. All right. There's my graph. Domain, x in the set of reals. Exclude the asymptote at x equals 3, so x cannot equal 3. Range, same thing, y in the set of reals. Y is not equal to positive 2 at the horizontal asymptote. One more. Oh, this one's going to be fun. I can already tell we have double asymptotes. Horizontal asymptote is y equals 0 because the degree of the numerator is less than the degree of the denominator. So y equals 0 is my horizontal. Vertical asymptotes, you might be able to come up with this in your head. More power to you. X squared minus 4. I'm going to set it equal to 0 and I'm going to find them. I'm going to add 4 to both sides. That's going to be x equals positive 4. Excuse me, x squared. I'm going to square root both sides and I'm going to get x equals plus and minus 2. So let's start by graphing these. I have y equals 0, which is going to go straight across the x-axis. That's my horizontal. I have a vertical at negative 2 and a vertical at positive 2. This ought to be an interesting graph here. I'm going to find a y-intercept. So y-intercept, I'll just do that right here, y-intercept. And again, we're going to do this math in our head because plugging in 0 to the function 0 squared minus 4 is negative 4. I end up with 2 over negative 4, which is negative 1/2. Alright, so at 0 I'm at negative 1/2. Alright, x-intercept. Now, I'm going to show the work here, but again, if you remember what I talked about earlier, x-intercept, plug in 0 for y, equals 2 over x squared minus 4, cross multiply, 0 times x squared minus 4 is 0, 1 times 2 is 2. 0 definitely does not equal 2. This implies that there is no x-intercept on my graph. That's okay. Doesn't matter to me. I'm good with that. Alright, so we definitely need some other points. So this time our t-table needs to include a couple to the left of negative 2, a couple to the right of positive 2, and I might even do some in between. So here we go. We're going to need a little bit of space here. X, Y, we're going to do our t-table like this. So starting on the left side, I'm going to do negative 4, then I'm going to do negative 3, then I'm going to do negative 1, positive 1, 3, and 4. Okay? Alright. So if I plug in negative 4, I get 1/6. If I plug in negative 3, I get 2/5. If I plug in negative 1, I get negative 2/3. If I plug in 1, I get negative 2/3. Well, that works out nice, doesn't it? If I plug in 3, I get 2/5. Oh, look at that. What do you think we get if we plug in 4? We get 1/6. This is going to be an interesting graph here. So at negative 4, let me grab some other color here. So at negative 4, I'm up 1/6. At negative 3, I'm up to 2/5, which is right there. So you can see where the curve's headed. It's heading up against the asymptote, just like that. While we're at it, let's do the right side. At positive 3, I'm at 2/5. At positive 4, I'm at 1/6. And the graph's doing the exact same thing. It's almost a reflection, or it is a reflection, over the line x equals 0, right over the y-axis. In the middle, I've got negative 1, negative 2/3, which is just a little bit below on the right and left of that y-intercept. So on the bottom, what's happening is it kind of looks like a little parabola action going down here. It's not really a parabola, but it's got some action like that. All right? And that, ladies and gentlemen, I believe, is the end of that lesson. See you on the next one.